Okay, so this is the review for dynamics test number 2. So problem number 1. This conveyor belt is moving at 4 meters per second. If the coefficient of static friction between the conveyor and the 10 kilogram package B is mu s is 0.2, determine the shortest time the belt can stop so that the package does not slide on the belt. All right, so there's no sliding on the belt. There's no sliding. And, it only gives us mu s of 0.2. But it's asking for the shortest time. It's like this extreme value. What's the shortest time that the package does not slide on the belt? So it's really kind of telling us, the force of friction between the conveyor belt and the package is going to go all the way up to its maximum at what mu s times n. All right, so let's draw this free body diagram for package B. So we've got this free body diagram for B. We've got the weight of B acting down 10 times 9.81. We've got the normal force N acting up, and then the block is going 4 meters per second to begin with, but the conveyor is slowing down. The conveyor belt is stopping it, and that force of friction is what is slowing it down, is what is slowing the package down. And so if we're trying to find the shortest time, the extreme value, that force of friction is going to be equal to mu s times n. And then once we find that maximum force friction, we'll kind of see what we're doing. Remember, this is problem number 1. This is like a kinematics problem, or kinetics problem, where we're drawing a free body diagram and having some of the forces equals mass times acceleration, right? So if I'm calling this x and this y, then I can sum the forces. I'm going to do y first. Some of the forces in the y direction would be, let's see, I've got n, and then I've got minus 10, 9.81 is equal to, and it is, I'll go ahead and put mass times acceleration, but it is not accelerating in this direction. So if n minus 10 times 9.81 is equal to 0, then from this n is 98.1 newtons. Then to kind of use that in my sum of the forces in the x direction. So sum of the forces in the x direction, the only force in the x direction is that force of friction, that 0.2 times n. I'm going to go ahead and plug that in. So that equals mass times acceleration. So I'm really kind of finding the extreme value for the acceleration, right? I'm setting that force of friction up to its maximum. So this is the maximum acceleration, really kind of deceleration if my block is moving to the left and this acceleration is to the right. So the maximum acceleration in the x direction is 1.96 meters per second squared. So that is the maximum. That's kind of what will make the block stop the fastest. All right, so now I'm going to use that. And, if I'm at the maximum, that this is going to be a constant acceleration. So I can, think about what I have. I've got like a V initial is 4 meters per second. A V final is 0, right? It's going to stop. The acceleration is, I've got to pick one direction to be positive, one direction to be negative. If my velocity is in, let me just be consistent. I'm going to say my velocity is in the negative 4 meters per second. So my acceleration is positive 1.96 meters per second squared. And so what is the time? Time is what's really asking for. So this velocity, this constant acceleration equation, Vf is equal to Vi plus At. So V final is 0 equals negative 4 plus 1.96 times t. And so from that, we would get a time of 2.04 seconds. And that is what it was asking for. Okay, so let's look at this problem right here. It says the coefficients of static and kinetic friction between the 20 kilogram block A and 100 kilogram block B are 0.4 and 0.3 respectively. All right, part A. Determine the maximum force P, or the maximum force that P can have such that the blocks A and B move together with the same direction. So if they move together with the same acceleration. So if they're moving together, then there's no sliding in between these blocks. There's no sliding in between here. And if we want to find the maximum, right, this sort of extreme value for P, then we're going to kind of set, okay, well, maybe the force in between A and B is to its maximum, is to, you know, up to that mu s times n. All right, so part A. To determine the maximum force P can have such as blocks A and B move together with the same acceleration. So let's I'm going to draw this free body diagram of them as if they were one block, one 120 kilogram block. So what would its free body diagram look like? Well, we would have the weight acting down, the normal acting up, and in this case we would have P and P right there. So looking at them together, summing the forces in the x direction, I'm calling x to the right, would be 2P, and that would be equal to 120, right? Sum of the forces in x equals mass, 120, times acceleration in the x. All right, so I've got that's one equation that I've got. If they're moving together, then that 2P is equal to 120A. Kind of all I can get from that one. Now, I need to separate them, break them apart. Look at either A or look at B. I'm going to break them apart, and I'm going to look at A. So breaking them apart and looking at A, I've got the weight of A, and I've got the normal of B pushing up on A, and then I have 2 P's, and then I've got the force of friction. All right, so that's my free body diagram using the same x and y axes. That's my free body diagram, and this is not really a problem where you've got mu s and you've got mu k, and so you have to determine is it slipping or is it not slipping. This is already worded to tell us that we know that it is not slipping. They are moving together with the same acceleration. So they're moving together with the same acceleration. But I am trying to find the extreme value, right? You know, this maximum force. So I'm going ahead and setting that force of friction equal to the extreme value mu s times n. All right, but but what are we still doing? We're drawing a free body diagram. Sum of the forces in x equals mass times acceleration in x. Sum of the forces in y equals mass times acceleration in y. So here I'm looking at, so here's just some new equations. Looking at, I'm going to go ahead and do the y direction so that I can get that in. So sum of the forces in the y direction would be, I've got the weight looking down, so negative 20 times 9.81 plus n is equal to mass times acceleration, and the acceleration in y is 0. So n would be 196.2 newtons. All right, and then summing the forces in x would be, I have 2p, and then I've got minus mu s times n, 196.2, and that equals mass, its mass. I'm only looking at A, right? I'm only looking at the free body diagram for A, so I only need the mass of A times its acceleration in the x direction. And so this equation that I have starred right here right, with 2 stars that I got from looking at the free body diagram for A, and this acceleration that I have right here, looking at the free body diagram of them together, 2 equations, 2 unknowns. I can write one in terms of the other, right, like P is equal to 60A, and then plug that in right there, or I could have just gone ahead and plugged in 2P for 2P right there, and I would get the acceleration, if they're moving together, 0.7848 meters per second squared. So that's kind of the maximum acceleration, kind of the extreme value for the acceleration if they're both moving together. And the extreme value for P max, just from these 2 equations, 2 unknowns, 47.09 newtons. All right, so that is part A. For part B is a completely separate problem. Part B, I'm going to kind of start afresh. So for part B, it says, it goes ahead and tells us P is equal to 200 newtons. So P is 200 newtons. Determine the acceleration of A and the acceleration of block B. Okay, so let's say that I didn't have part A. Let's say that I didn't have part A. If this problem had just given this, and if it had just said if P is equal to 200 newtons, determine the acceleration of A and the acceleration of block B, then I would need to show if it is slipping or not, right? I would need to show, are A and B moving together, or is A slipping on top of B? So make sure you can do those types of problems. We don't have any of those problems on this review right now, so make sure you can do those types of problems where you don't know whether A and B are moving together, or maybe A is slipping on top of B. With those, you need to show if it is slipping or not. So review those types of problems. Make sure you can handle those. But we're kind of lucky in that from part A, we already knew that P max was 47.09 newtons. And so now if P is 200, then I know they are slipping. So once I prove that it's slipping, or once I know that it is slipping, then what do you do? So we know it is slipping. So what do we do? Well, we can't look at a free body diagram of A and B together. That doesn't work anymore. A and B are not moving together, so don't draw them together. So I need to look at a free body diagram for A or a free body diagram for B, and maybe even have to look at both of them. So I'm going to start with the free body diagram for A. So looking at A, I've got the weight of A acting down. I've got the normal force of B pushing up on A. I've got 2 P's. Both of those are 200 newtons. And I've got the force of friction right there, which I do know is what? Well, I know that it is slipping, so I know that the force of friction is mu K times N. Okay, so, once we have a free body diagram, what do? Sum of the forces in X equals mass times acceleration in X. Sum of the forces in Y equals mass times acceleration in Y. I'm going to start with summing the forces in Y so that I can find N. So summing the forces in the Y direction, again I'm calling X, Y, summing the forces in the Y direction would be the normal of B pushing up on A minus the weight, which would be 20 times 9.81, and that equals, it is definitely not accelerating in the Y direction. So normal of B pushing up on A is 196.2 newtons. And so then summing the forces in the X direction, that would be, I would have 400 newtons minus mu K times N, 196.2, and that is equal to mass. I'm only looking at A, only looking at the free body diagram for A, times the acceleration of A. right? This is just the acceleration of A. So the acceleration of A would be 17.06 meters per second squared. All right. So that is the acceleration of A. Now I need the acceleration of block B. So let me draw the free body diagram for block B. So just looking at B, this is how I like to do it. I'm going to say I've got the weight of B acting down. I've got the normal force of the ground pushing up on B, and I have the normal force of A pushing down on B, which is the same as B pushing up on A, right? This NBA is the same as NAB. And then I don't have any P's. The P was only acting on block A, but on B, I have the force of friction. I have the force of friction between A and B. Force of friction between A and B is going to be equal and opposite, right? This force of friction is going to be equal and opposite this force of friction right here. So here I've got a force of friction, and it is 0.3. It is mu k times n. It is the n in between A and B. It would be the n right here. This n of B pushing up on A or A pushing down on B. It would not be the n of the ground pushing up on B. All right, so it would still be this 196.2. All right, so now I can sum the forces in the x direction. Would be the only force in the x direction, 0.3 times 196.2. And that would be equal to mass. Remember, I'm looking at free body diagram for B, so only the mass of B times the acceleration of B. So here the acceleration of B is 0.59 meters per second squared. And does it kind of make sense that the acceleration of A would be very large, the acceleration of B would be smaller, but B would still go to the right a little bit. But definitely not as much as A is accelerating to the right. Whereas if we look at the previous part A, we said that both of them were moving with an acceleration of 0.7848. So if they were moving together, they would both move with an acceleration of 0.7848 when you had that, or that was the maximum. But once A started sliding on top of B, we ended up with this scenario where A is moving at 17.06 meters per second squared, and B is moving at 0.59 meters per second squared. All right, so let's look at this problem. Blocks A and B each have a weight of 10 pounds. At this instant, block B is moving downward at 2 feet per second, and theta is 45 degrees. Block A and the quarter circular ramp has coefficient of kinetic friction of 0.3. Find the tension in the cable using free body diagram and particle kinetics. All right, so my first instinct is this is a constrained motion problem. I see a rope, I see two blocks. Maybe I need to write L total is this and take the derivative. Maybe I should do that. But if I said L total, that would be LB plus LA, and then taking VB plus VA, and the acceleration of B plus acceleration of A. Of course, all these would be the tangential of A. If I did it this way, and if I had this equation and I wanted to use it, then I did all of these as positive out. And so moving down, moving further, I would need to have all of my equations to be positive out. But it's just one rope. maybe I'm just overthinking it by thinking this is a constrained motion problem. It's just one rope. That rope has to be going with the same velocity, the same acceleration. And so I think I'm just going to say, the acceleration of B down is going to be equal to this acceleration of A in that direction. Whatever velocity I have of B would be the velocity of A. So I think I'm just going to say, this direction is positive. And then I just have one acceleration, right? And I just have one V. So I'm just going to say this is positive, and I don't have any B's or A's. I just have one acceleration, and I have one velocity. All right, so we're going to be doing free body diagrams. We're going to be doing particle kinetics. Let me draw the free body diagram for block B. So for block B, I've got the weight of B, and I've got the tension in the cable. And I'm going to say this is positive Y. So summing the forces in the Y direction would be the weight of B. What is the weight of each? Have a weight of 10 pounds. So 10 minus tension is equal to mass. So take the weight divided by 32.2 times the acceleration. That's the A. That's the acceleration of B. That's the acceleration of A. They're moving together. All right, so there's one equation. Put a star by it. And now I'm going to look at the free body diagram for A. The free body diagram for A, it is drawn over here. It is this on the incline A, and I have tension right there. I have a normal force of the incline pushing up on A. I have the weight of A, and I have the force of friction, and I already know it's moving. And it told me this mu k of 0.3. So this force of friction is 0.3 times that N. All right, what do I want to identify as my, or what direction do I want to define my axes as? Well, A is definitely in a circular path. If anything is in a circular path, you need to have the normal direction to point into the curve, and you need to have the tangential direction to point, in the direction that it is traveling. So these are gonna be my axes. Luckily, these 1, 2, 3 forces align along those axes. This W does not, but we're lucky that it's 45 degrees. So that's that 45-degree angle right there. So summing the forces in the tangential direction, summing the forces in the normal direction, summing the forces in the let me start with the normal direction. Summing the forces in the normal direction, I would have negative N is away from the normal direction, and then plus the weight, which is 10 cosine 45, and that is equal to, now, is it accelerating in this direction? Let's be careful. Yes, it is accelerating because it's the normal direction. It is accelerating at mass. So there's its mass times acceleration. So normal acceleration is v squared over rho. And so it told me already that the velocity at this instant was 2. So square that over rho. My units work out if everything's in feet. Everything's in feet per second. Everything's in pounds. That 32.2 is feet per second squared. So that does work out. So from there, I would get an N is 6.95 pounds. And then some of the forces in the tangential direction. Some of the forces in the tangential direction would be equal to, I've got tension in the tangential direction. Then I've got minus the force of friction, 0.3 times N, 6.95, I just found. And then minus a portion of the weight, 10 sine 45 is in the negative tangential direction. And that equals mass times acceleration. And that is the acceleration of B, that's the acceleration of A. I just have one acceleration because I'm defining all my accelerations as the same. And so I have another equation right here. So I've got this equation with 2 stars, this equation up here with 2 stars. Write one equation in terms of the other, one unknown in terms of the other. Substitute, solve in. So you should get, let's see, we should get that the acceleration of both of them is 1.37 feet per second squared, but it asks for the tension. The tension would be 9.58 pounds, and that's what it asked for. All right, so let's look at the next problem. So this package has a weight of 5 pounds and slides down the chute. When it reaches the curved portion at A, theta is equal to 0 degrees. So this is where this problem is defining its theta as kind of starting right here. So it reaches point A. It's traveling at 8 feet per second. If the chute is smooth, all right, so no friction, determine the speed of the package using free body diagram and particle kinetics. When it reaches an intermediate point C, theta is 30, and when it reaches the horizontal plane, and also find the normal force on the package at C. All right, so a lot to think about here. But, I need free body diagram. I need particle kinetics. So I'm going to draw my free body diagram up here. So here's a free body diagram at A. And let me kind of draw this at any angle. Not at one specific angle, but at any angle. I would have the weight of A acting down. I would have the normal force of the incline pushing up on A. And that's it. And my directions would be a tangential direction and a normal direction, right? This would be into the curve. And so now this angle right here, between the weight and T, I'm going to need to find that so I can use, sine and cosine in my free body diagrams. But that is not really theta. That angle is not really theta. This becomes a little bit tough here, but this. All right, so that would be. I'm going to call this beta. Beta is the angle that this line is from horizontal. That's what this beta is. And so beta and theta are going to be off by 30 degrees, right? I'm sorry. Beta and theta are going to be off by 45 degrees. So beta is going to be equal to theta plus 45 degrees. Does that make sense? When theta is equal to 0, then beta is 45 degrees. But anyway, so that they are off. So that's the tricky part about this problem is that this angle right here is not theta. It's something different than theta. So let's call it beta. Let's kind of forget everything about theta for now. Let's call it beta. Okay, so there's my free body diagram. I drew the normal and tangential directions. Let's sum the forces in the normal and tangential direction. Summing the forces in the tangential direction. All right, what is in the tangential direction? Well, a portion of this weight of A is in the tangential direction. The weight of A is 5, and 5 cosine beta is the force in the tangential direction. And that would be equal to mass, 5 over 32.2, mass times acceleration. All right, so I kind of have my acceleration in terms of beta. All right, that's interesting. So maybe, I know it starts at 8 feet per second. Maybe I can use the acceleration to find, what it ends at. And that's exactly what I'm going to do. And that is not a constant acceleration, right? That is changing. It has a beta, so that's acceleration in terms of beta. How do I handle that? Well, I know the integral of v dv is equal to the integral of a ds, but this I can change to a ds d beta, and this is going to be rho. I kind of went over this in class. I think you can kind of just kind of memorize that if you've got something in the normal tangential direction and you're trying to find the integral v dv equals integral ads, you can change ds to this rho. You can kind of change this ds to rho d, whatever angle this is here in your free body diagram. All right, so let's use that. All right, so integral of v dv would be v squared over 2 from v initial to v final. And that is equal to this integral of 32.2 cosine beta times rho. And rho is this constant 20 feet. So the integral of 32.2 times 20 times cosine beta would be this is equal to 644 sine beta, as beta goes from beta initial to beta final. And so this, if I'm interested in the velocity, the question asks for what is the velocity at an intermediate point where theta is 30. That is sort of, that is what my beta, if my theta is 30, my beta, what I'm calling my beta, would be 30 plus 45, so it would be at 75 degrees. And it started at 45 degrees, and it started with this velocity of 8 feet per second at that 45 degrees, and so I'm looking for the final velocity right there. So plugging in these right here to solve for the velocity, we would get the velocity final when it is at point C would be 19.9 feet per second. It also asks for the velocity at point B. So the velocity at point B, I've got the same equation, VF is equal to 644 sine beta from beta initial to beta final. So here I'm looking, it starts at 45 degrees, it starts with a velocity of 8. I'm looking at a beta, what I'm calling beta, of 90 degrees. What is its velocity? So plugging that in minus that, plugging that in minus that, I would get a velocity final at point B equal to 21 feet per second. It also asked, it said also find the normal force on the package at C. So let me look at the normal force on the package at C. So let's look at C, kind of draw this free body diagram if we were at C. So at C, this free body diagram would look like N right here. It would look like the weight right here. And again, this is normal, this is tangential. This angle would be a beta, but that angle would be 75. If I'm only interested in something just at one specific point, I can go ahead and plug in that angle right there, that angle of 75 degrees. And if I sum the forces in the normal direction, look, I drew a free body diagram. I'm going to sum the forces in the normal direction. Summing the forces in the normal direction would be N minus the weight, a portion of the weight would be minus the weight, which is 5, 5, and that would be sine 75. Sine of 75, and that would be equal to mass over 32.2 times acceleration in the normal direction. And this acceleration in the normal direction is v squared over rho. And at this point, at this intermediate point C, the v would be 19.9 squared over 20. So I've got everything except for n. So I would get that n would be 7.91 pounds. Okay, so this review problem. I've got a 2 kilogram ball of negligible size fired from point A with an initial velocity of 10 meters per second up the smooth inclined plane. Using the work energy method or the conservation of energy method, determine the velocity of the ball just before it leaves the edge at B and the velocity of the ball at D. Also determine the distance from point C to where it hits the horizontal surface at D. So I can use either the work energy method, which would be the work energy method would be kind of organize my problem in such a way the sum of all the work done from 1 to 2 is equal to delta T, or the conservation of energy method, which is what I like to do, which is what I'm going to do, is like potential and kinetic energy plus any non-conserved work initially would be equal to potential plus kinetic energy final. So this is how I'm going to organize my problem. So I like to kind of write that out. The potential energy initially plus kinetic energy initially plus any U prime, any non-conserved work done by external forces is equal to V2 plus T2. Or in this case, why don't I say VA, TA, any non-conserved work from A to B is equal to VB plus TB. This V could have both gravity and spring. This potential energy could be both gravity and spring. But of course I don't have a spring right here, so that potential energy is only due to gravity. So, potential energy due to gravity is mgh, 1/2 mv squared. I don't have any external forces which do work. The only other force I can think of here would be the normal force, but that normal force doesn't do any work because the displacement is always perpendicular to the normal force. So I don't have any work done right here. So that is equal to mgh2 plus 1/2 mv squared 2. So let me say the mgha, the 1/2 mva squared, is equal to the mghb, 1/2 mvb squared. All right, so for mgh, I need to, I've always got to be positive up, but I can set my 0 point to be wherever I want it to be. I think I'm going to set this right here to be my 0 point. That way, this height at A is 0, but the height at B is going to be 1.5 meters. Okay, but anyway, so this is 0 right here. 1/2 mass, let's see, from the problem statement it said it was a 2 kilogram ball. And it told me that the velocity of A was 10 meters per second. And so this is equal to mass times gravity times the height at B of 1.5 plus 1/2 mass times velocity at B squared, which I don't know. I have one equation, and luckily I only have one unknown. So from this, I could get that the velocity at B is equal to 8.4 meters per second. So that was one thing it asked for. velocity at B is 8.4 meters per second. It also asks for the velocity at D. So I can, go from all the energy from A to D, or the energy from B to D, B to D. But any way I do it, I'm still going to be doing this conservation of energy, VA plus TA plus any non-conserved work, now this is VD, TD. All right. So the left-hand side of this equation stays the same. That's 0. So the left-hand side of the equation still stays 1/2 to 10 squared. Now the right-hand side of the equation would be, now there is no height, right? So now the height at D is 0. So the potential energy at D is 0. It only has 1/2 m velocity at D squared. And so here the velocity at D is 10 meters per second. Okay, and I use conservation of energy for that. It needed me to find this distance D. It also said, determine the distance from point C to where it hits the horizontal surface at D. It needs me to find this distance here. Well, there's nothing in my conservation of energy equations to solve for that distance D. This is going back to being a projectile problem. So this is really a projectile from B to D, right? This is a projectile from B to D. And I know all the information at B. I know that the velocity at B is 8.4 meters per second. So this is a new problem. I've got a projectile that starts up at B. It starts with a velocity of 8.4 meters per second. And so I need to find the distance D. So I'm going to look at this as a projectile problem. All my projectile problems, I separate X and Y. So I'm going to do that. I'm going to separate X and Y. Let me do this. I'm going to separate X and Y. X from Y. And I could list out some of my things, my initial conditions, my what I do know. One thing that I need to kind of figure out is the direction of that velocity, right? I know that the velocity at B is 8.4 meters per second, but what direction is it? Well, it is, along this incline, it has this velocity of B of 8.4 meters per second. But what direction is that? Well, let me look at this incline. The incline is over 2 up 1.5. So it is at this 2, 1.5, and that would be 2.5 direction. So that is the direction. That's kind of the angle of the velocity. So my projectile problem, I'm always using this constant acceleration equation. SF is equal to SI plus VIT plus 1/2 AT squared. And in the y direction, SF in the y is equal to SI in the y plus VIT plus 1/2 AT squared. So plug in what I know. The final, the initial, it starts at 0 in the X and it ends at D. It starts at 8.4. 8.4, but the component that is in the X direction would be the 2 over 2.5 component times time, and there's no acceleration in the X direction. So I've got one equation. I've got D is equal to something T, and then over here on the Y side, if I think about the Y direction, what position does it end at? It ends at 0. It started at 1.5. It had an initial positive velocity of 8.4. 8.4, the 1.5 over 2.5 component, plus 1/2 negative 9.81 times t squared. So from this equation, I can just go ahead and solve that my time is 1.27 seconds. Then I can plug that in right there to get my distance of 8.53 meters. And so that is the distance that it does. So sometimes in these problems, you might have what we had right here. We had a projectile problem at the end of one of our conservation of energy method problems. That's perfectly fine to have that. Okay, so this problem, we have this roller coaster, has a mass m, it's released from rest at point A. If the track is designed so that the car does not leave it at B, right, obviously we would want the cart to reach this point B, to get up here without leaving the track. Determine the required height H, required height that A needs to start from so that the car does not leave it at B. Also find the speed of the car when it reaches point C. I'm going to use either work energy method or conservation of energy method. So, if you feel comfortable using the work energy method, the sum of all the work done from 1 to 2 is equal to delta T. But I like to use conservation of energy, just V1 T1 plus U, the non-conserved work, is equal to V2 plus T2. So, if I don't know where to start, I'm going to use conservation of energy method. Maybe I'll start with that. So let me kind of look at that and start with that. So I'm kind of looking at it from A to B. So from A to B, I'm going to have this potential at A plus kinetic at A plus any non-conserved work from A to B is equal to potential at B plus kinetic at B. So here, this could be gravity or spring. This could be gravity or spring. When you have potential energy, we have two things that can have potential energy. Don't have a spring in here. All right, that's fine. All right, so I've got the MGH at A, which I don't know, plus 1/2 MV at A, but I kind of forgot that this was V squared. This was 0, right? It started from rest. So that's what I have on the left-hand side of the equation. I have no forces I have no non-conserved work forces. So that is equal to the MGH at B, which I do know. That is 20 plus 1/2 MV at B squared, which I don't know. So, if I'm looking at this equation right here, I only have one equation, so I can only solve for one thing. But, let me see. The mass drops out. I can divide mass out of all four of those equations, but I've got 9.81 times the height at A, which is H, which is what I'm looking for. That is equal to 9.81 times the height at B, which is 20, plus 1/2 times the velocity at B squared. All right, what is the velocity at B? It is not 0, okay? If it barely makes it up to B, it is not 0. But what do we know if it barely makes it up to B? If it barely makes it up to B, then I don't really have any more of that track pushing down on it at B. I don't have any of this normal force. If it barely makes it, then this normal force of the track pushing it down is equal to 0. It is almost going to leave the track, right? So I set that normal force equal to 0. But what else do I have? So let me look at the free body diagram for the roller coaster at B. The free body diagram for the roller coaster at B. I have the weight, mg, acting down, and that's it. But I notice that it is in a circular path, and so I define my axes as normal and tangential. And so summing the force in the normal direction would be equal to mass times gravity, and that is equal to mass times the acceleration in the normal direction. And the acceleration in the normal direction is v squared over rho. The rho is 7.5. So the velocity that it needs to have in order for it to barely make it up there and for it to almost leave the track, but not quite, the velocity that it needs, the velocity at B needs to be 8.58 meters per second. So that's sort of what I was missing. This right here was what I was missing in that equation in order to solve for H. Okay, so if something is barely making it or about to leave the track or about to fly off, we set that normal force of the ground pushing up on it, or of the, in this case, of the track pushing down on the roller coaster. We set that normal force to 0. Sum the forces in that direction equals mass times acceleration in that direction to find that velocity. So in this case, it needs to have at least a velocity of 8.58 meters per second in order for it to make it up there. All right, so going back to this equation, plugging in 8.58 right up here in that, I would get a height to be 23.75 meters. All right, so that's the minimum, the bare minimum required to let it go over that loop without falling off. All right, then at the end of the equation, it says, at the end of the problem, it says also find the speed of the car when it reaches point C. So I'm going to use conservation of energy I could do it from A to C, I could do it from B to C, I can do it for whichever I want to. I'm going to do it from A to C. So from A to C, I'm going to use conservation of energy. VA, TA, don't have any work, is equal to VC, TC. So for that, it started from rest, so the kinetic energy is 0, but it did have an mgh. So it did have an m. I'm not really told the m, but I'll just plug that in. And then the height, 23.75, and that is equal to, so when it is at C, the height is 0. It doesn't have any more potential energy. The mgh is 0, and so here the kinetic energy will be 1/2 mvc squared, but the masses can cancel out. And here I can get the velocity of C, 21.6 meters per second. All right, so this problem, a 10 kilogram package drops from a chute into a 25 kilogram cart with a velocity of 3 meters per second. Knowing that the cart is initially at rest and can roll freely, determine the final velocity of the cart and the impulse exerted on the cart by the ground. So this, talks about impulse, and I can see that there's a collision, right? This package is going to collide with the cart. So I need to use momentum, right? Conservation of momentum. So conservation of momentum, the initial momentum plus any impulse, I'm going to say, a force times T, is equal to the final momentum. You could rearrange that, write that however you want to. That's how I like to do it. The initial mass times velocities plus any impulse given by an outside force is equal to the final mass times velocity. So I'm going to look at this block and this cart as my two objects. And I'm going to look at their total momentum before, right? The mass of, I'll call this package, I'll say mass of the block and the cart C here, the mass of the block, velocity of the block, and the mass of the cart times the velocity of the cart, all that momentum initially, plus any impulse by an outside force, right? This is impulse by an outside force is equal to all the mass of the block, velocity of the block, and the mass of the cart, velocity of the cart afterwards. Okay, so the 10 kilogram block hits the cart, and they both, do you see that they are, this is going to settle on the cart, and they are both going to be going together to the right at the same velocity. So this right here, I'm going to combine these, right? I'm going to say the mass of the block and the mass of the cart are both going at some velocity, final. Okay. All right, so knowing the cart's initially at rest, can roll freely to determine the final velocity of the cart and the impulse exerted on the cart by the ground. Now remember that this is a two-dimensional equation. This equation is true in x, and this equation is true in y. So I'm going to break those apart and separate those. So I'm going to only look at the mass of the block times the velocity of block in the x initially, plus mass of the cart, velocity of the cart in the x, plus any impulse by an outside force in the x direction is equal to mb plus mc velocity in the x direction. Okay, so the cart. Initially, the cart had a velocity of 0. It started from rest. An impulse by an outside force. What could create an impulse? What could create an impulse? A force times time. What could create an impulse? Well, B does create an impulse on the cart C, but C pushes back, right, with an equal and opposite impulse. And so since I'm considering both of those, both of the block and the cart in this equation, that's kind of like an internal force. If I think about the impulse, then I need to think of the negative impulse of the cart pushing back on B. But one outside object that is creating an impulse is the ground, right? The ground is pushing up on the cart. The ground is putting an impulse into this problem. All right, so I do have an impulse by the ground, but that is not going to be in the x direction. That is only going to be in the y direction. There is no outside force creating an impulse on my system in the x direction. All right, so let me plug in everything I have. So the mass of B, it's a 10 kilogram package. The velocity of B in the x direction would be 3 cosine 30 in the x direction. So that would be the m times v. This term is 0, this term is 0. This would be equal to, so when they're combined together, the 10 kilogram package and the 25 kilogram cart, it's like they have a 35 kilogram mass and its velocity. So from this, the velocity in the x direction, both of them going with velocity of 0.742 meters per second. Okay. So that I got that from x. If I look at y, I can get the answer to the second part of the problem, which is what is the impulse exerted on the cart by the ground. So the mass of B, velocity of B in the y, plus mass of C, velocity of C in the y, all of this initial, plus the force in the y times time, right, the impulse in the y, would be equal to, they're moving together, times the velocity in the y. So let me look at that. The velocity in the y is 0, right? They are both moving together to the right, moving together in the x direction. So that velocity would be 0. This one started from rest, so its initial velocity is 0. So initially I start with 10, and its velocity is 3 sine 30, and it's actually down, right? I want it to define my y as positive up, so that is down, plus any impulse is equal to 0. So the impulse, I'm just going to leave it as f times time. Leave it as f times time. I'm going to call that impulse. I don't know don't think the book actually gives it a variable name. This impulse would end up being, if I take 10 times 3 sine 30, would end up being 15, and it's a force times a time, 15 Newton seconds in the positive y direction. All right, so another impact, collision, another impulse momentum problem. So in an intersection, car B was traveling south, car A was traveling 30 degrees north of east when they slammed into each other. Upon investigation, it was found that after the crash, two cars got stuck and skidded at an angle. Both of them went at this together at this angle of 10 degrees north of east. Each driver claimed he was going the speed limit of 30 miles per hour and that he tried to slow down but couldn't avoid the crash because the other driver was going a lot faster. Knowing that the weights of car A and B were 3,600 pounds and 3,800 pounds respectively, determined which car was going faster and the speed of the faster of the two cars if the slower car was traveling at the speed limit. Okay, so this is, I see a collision. This is an impulse problem. I'm going to use conservation of momentum, right? And that is that the mv initially plus any impulse by an outside force, not an internal force, not an impulse, of the objects I'm looking at, is equal to mv final, or the momentum final, right? So what I'm really doing is the mass of A, velocity of A, and the mass of B, velocity of B. And there's no outside force giving any impulse. So this is really just conservation of momentum. This would be equal to the mass of A, velocity of A, plus mass of B, velocity of B. But this is all initial. This is all final. And they move together, right? So really I've got mass of A, velocity of A, plus mass of B, velocity of B, all the momentum initially, and mass of A plus mass of B. They're moving together at a velocity, at the same velocity. But this is in 2D. This is really two dimensions. It's really two equations. So let me write those. Let me separate those, right? I have an x equation. So the mass of A would be 3,600 divided by 32.2 times the velocity of A. So velocity of A initial, I don't know it, but I know that the x component of velocity of A would be cosine 30. And the mass B, velocity of B in the x direction, B is not traveling in the x direction. So initially, it has no velocity in the x. It has no momentum in the x. So that would be equal to, so the final, on the right-hand side, they're moving together, stuck together, 3,600 pounds plus 3,800 pounds are stuck together, divided by 32.2, times, I don't know their final velocity, but I do know that it is at this angle of 10 degrees. Right, so I have that the velocity of A, so I have two unknowns in here, the initial velocity of A and the velocity final, but maybe I'll go ahead and write one in terms of the other. I would have 96.83 VA is equal to 195.74 V final, maybe write VF, well, let me not do that just yet. All right. But anyway, two unknowns in that one equation. Can't solve right away. Maybe leave a little bit of room and go to the y equation. The y equation. The mass of A times the velocity of A. I don't know it, but I know the sine 30 would be the component in the y direction. And now I've got the mass of B, 3,800 divided by 32.2, times the velocity of B. I don't know it, but I know all of it is in the negative y direction. All right, I'm gonna say y is positive up. So my velocity in the y direction would be negative VB. And this equals those stuck together times the final velocity sine 10 would be the one in the y direction. I don't have, I've got another equation, but I kind of added another unknown. But let me see if I really want to compare, right? Determine which car was going faster. Determine which car was going faster. So I want to compare VA and VB. A couple different ways you can do that, but let's from this right here, let's write VF in terms of VA. You would get VF is 0.495 VA, and then I could plug this in right here, and then I have an equation, and the only things in my equation are VA and VB. I would have just a little bit of math, so simplifying this a little bit, 55.9 VA minus 86.96 VB is equal to 17.07 VF. And then if I plug in 0.495 right here, I could end up with an equation that said VA is 2.24 VB. All right, I've got an equation that says VA is 2.24 VB. So which one is faster? Well, no matter what they are, VA is 2 over 2 times VB. So car A was going faster. So car A was going faster, and if I guess that, if I assume that VB was, if the slower car, I think that's what the problem statement said, determine the speed of the faster of the two cars if the slower car was traveling at the speed limit. So the slower car, if VB was traveling at 30 mph, then VA, if this was 30, then VA would be 2.24 times 30. VA was at 67.2 miles per hour. So VA was the one that was traveling a lot faster than the speed limit.